Hello everyone, welcome back to the channel. Today I am absolutely honored and proud to announce that we finally surpassed 25,000 subscribers. It's been about 2 years of work getting to this point, and I'm very proud of that. Also especially far more proud for all of you who have actually gotten good results out of watching the videos on here, which at the end of the day is a lot more important to me than any subscriber count. I'm going to keep this thing pretty short and sweet, mainly because I ate a bunch of chili at my work's happy hour, and if I take too long to make this video, I'm going to have to poop in the middle of it. So let's hope that doesn't happen. I really thought this video was kind of going to be a wash. I was like, oh, Reddit comments, you know, that should be relatively easy. And then I spent the next few days trying to figure it out because it turns out it's not that easy. So let's go ahead and talk about it. Alrighty, let's see if I can get through this video relatively fast. I am fiending for an edible here. It is a Friday night and I am tired. So, what are Reddit comments? Well, technically, in this series alone, I've already made another video devoted to this. And that is true, it was in the Twitter video. However, I don't really think I went in nearly as much depth here as I could have. And I would like to try and cover all my bases in this 2.0 series. So let's go ahead and do that. So if you're not a big Reddit user like myself, because I have no life, this is somewhat what it looks like. You'll have your post at the top. You know, for example, I just reached 25K. That's worthy of a post. And then we've got some comments. And the interesting thing about comments is they can actually just be infinitely nested within one another. So for example, here we have Sydney Sweeney. She's okay looking, and she's calling me sexy. 100 upvotes. Everyone agrees with her. Kate Upton calls me smart. She's responding to Sydney Sweeney. And then Mark Zuckerberg says lies. Mila Kunis, on the other hand, is also agreeing with Sydney Sweeney and says take my upvote. And you can see we have these upvote and downvote counts over here, which is another very important part of Reddit. So actually, here are our formal problem requirements, because just the nesting of the comments itself is not so important, but actually Reddit is going to support a bunch of different ways of viewing the comments within a given post. So the first is going to be new, which is basically like, think of all of these types of defining comment orders as hierarchical. So basically first we would order all of the top level comments by the newest ones, and then, you know, when we're showing now the second comment, or like the second layer of comments within a top level comment, we're also ordering those by the newest one. So hopefully that makes sense, right? I'm going to pick the newest out of all the top level, and then within one comment, when I'm looking at the chain of comments that are responding to that, I also pick the newest there, and then on and on and on and on. Then we have hot, which is basically, you know, let's say within the last hour or so, what's gotten the most upvotes. We've got top, what's gotten the most upvotes in the entire history of the post. And also controversial, which is some factor or some calculation based on the number of upvotes, the number of downvotes, the number of total interactions, and basically, you know, probably a lot of upvotes and a lot of downvotes, totaling somewhere near zero. So like I mentioned, all of these are recursive, right? So, you know, not only do I want, you know, the newest post at the top, second newest, etc., but also within this guy, I now want the newest at the top, the second newest over here, and then within this guy, I also want the newest at the top, second newest over here. So hopefully that makes sense. It's all recursive, or at least that's how I'm choosing to implement it for this problem. Reddit, of course, can change things up as they please. Great. So the next thing we're going to do are some very brief capacity estimates. So that is actually going to be pretty relevant for this problem, because if in theory our posts or the number of comments on a post is, you know, boundless, and you know, you can have literally billions of comments and billions of inner comments on that post, well, we're not going to be able to put everything on a single partition, and then we're probably going to be in a lot of trouble in terms of scaling this thing out. So let's go ahead and actually do some quick mental math to try and figure out whether single partitioning per post at least is possible. So I did some quick Googling, and apparently there are 500,000 comments on the most popular Reddit thread ever. But since we're not soft over here, we're going to round up to 1 million and double that. The next thing that we're going to do is I'm going to assume that the average comment size is around 200 characters in length. Now that is probably going to be the majority of storage that we need to store a comment. However, there is going to be some other metadata like a user ID, a post ID, the time of the comment, the number of cumulative upvotes or downvotes, stuff like that. So I'm actually going to imagine that every single comment is going to take around 500 bytes to store in total. Cool. So that means that for a single post, if we just wanted to store all of the raw comments on it, that we could probably get away with doing so using 500 megabytes of data. Now the nice thing about that is not a lot. We can definitely get that on a single hard drive or within a single partition. And if we decided, for whatever reason, to completely copy all of those for our 4 in total comment views, that could be 2 gigabytes of total storage. And in theory, if we were able to keep those all on the same actual database node, that could benefit us in many ways as well. We might be able to avoid a 2-phase commit if we were writing to all 4 of those at a time. So, like I mentioned, it's likely going to be possible to store these on a single partition, which is huge for us. We'll still discuss what would happen if we couldn't, but yes, I think reasonably we can make that assumption. And then another thing is that let's assume that rather than denormalizing our data, right, and making 4 different copies for all of those 4 views, we decided to normalize it. So we had one source of truth view and then 3 secondary indexes that only included the comment IDs and their ordering. In that case, if we just needed the comment IDs, it's probably going to be about 8 bytes to store an ID, right? 64 bits or something like that, or a long. And then again, there might be up to 1 million comments per post. So now 8 megabytes. And the nice thing about 8 megabytes is that's not a lot of data at all. We could probably store that in memory, but we'll also cross that bridge when we get there. Cool. So let's think about some main considerations for this problem to also help us prioritize, what type of data flow we're trying to optimize here. Because it's Reddit, the majority of people are probably lurking. There are posts with a lot of comments, but I would say that even more so than that, most people are actually just reading and not commenting. And so again, if reads are going to happen much more frequently than writes, we do want to be prioritizing the read path. That doesn't mean that people don't comment at all. If we do have a comment, I don't want someone waiting 10 to 30 seconds for their comment to show up. It should show up relatively quickly, but at the end of the day, if it is like a very clear choice between our read speeds and our write speeds, we should probably optimize for reads. Cool. Like I mentioned, we don't want really bad writes. And then the biggest thing, which is going to become very important later on, is that even though we have 4 different comment views, they don't actually have to be perfectly in sync, as long as they're probably eventually consistent with one another, right? So the idea is, imagine we had our new view and it's showing that there's comment 3, 1, and 2, and then the top view shows that there's comments, 4, 1, and 2. That's actually not a huge deal, as long as eventually they're both going to be showing the same thing. We don't necessarily have to basically commit a comment to all 4 views at the same time. We can deal with some lag there. A user isn't really going to know, and even if they did, it's social media, they're not going to care that much. One thing that is particularly important, though, is that all of these views are going to be causally consistent so that the comments actually make sense. So when I say causal consistency, it means that if you have one comment that is being displayed on your screen and it relies on some parent comment, that the parent comment is also present, right? So I can't have comment 2 over here without comment 1 existing. If this guy weren't able to be here and we just saw comment 2, everyone would be like, well, why does this even exist? What's it replying to? And that would become confusing. So we do want to maintain causal consistency across all of our views. Cool. So the first thing that I'm going to touch upon now is this concept of a source of truth table. So like I mentioned, regardless of whether we have 4 different copies of all the comments or whether we have one source of truth table and 3 different secondary indexes, we are going to need basically one centralized data store where we can rely on the data and say, like, these are actually our comments for the post, right? This is not eventually consistent. This is it right here. Cool. So again, the interesting thing with comments in Reddit are that they are organized as some sort of tree. So as you can see right here, if we have a post, here's some top level comments. Maybe those have children. Maybe their children might even have children. And so generally we're almost thinking about this thing as like a big tree or possibly even a graph. I wouldn't say it's a graph. It is technically a tree, but I guess all trees are graphs, so you can say that. Cool. So the first thing that we're going to talk about is how we're going to build out this, just generic commenting table, or what I'm going to call the source of truth table. So I'd say we have 2 main options. The first is going to be actually using a graph database, because like I mentioned, trees are graphs. And so the nice thing about graph databases are that they're good at handling this data. The reason being that you actually use physical pointers on your hard drive from node to node. This is in contrast to something like a non-native graph database, where we basically just use a typical relational database index in order to abstract away the concept of the edge, right? So I would basically have a second table that represents an edge where I would have the primary IDs of the 2 nodes that are being connected. The problem with that is that as that table, our edges table, grows in size, the slower it is to actually find an edge because indexes grow logarithmically relative to the size of the table, and so non-native graph databases are sometimes not so great. However, in contrast, a native graph database is not going to get any slower as the table itself gets bigger. So like I mentioned, internally, basically if I have some post right here, we're also going to maintain a list of all the edge objects, which again would just be some address on disk, and then we can jump to those in O of 1 time. Now do note that just because we're jumping in O of 1 time doesn't mean that constant factor is fast, right? Jumping from place to place on disk objectively is pretty slow. You have to scan all over the disk, and so for this reason, ideally, if you can avoid using a graph database, you might want to. It's also sometimes pretty hard to scale them out if your data has to live on multiple different partitions, but ideally we can keep all of our data on one partition here as we discussed. So the way that we could kind of easily abstract things away here is if we have a post and then we have a comment, right? So I can give all of my edges increasing alphabetical sequences, so A for the first edge, B for the second, and then what we would do then is give each child edge another letter, A and B. So this way, I know if I want to go to comment AB, I can really quickly get there, basically linearly to the length of the ID of the node. I would just say first jump to A, then jump to B. And that's a lot better than having to run some sort of like depth first search every single time to actually find your comment. Cool. And if you're actually thinking about this, what's interesting is that the way that this graph works is that it's actually going to preserve the order that the nodes were written. Right? So if I were to load this entire graph, this is effectively the same as our new configuration for comments, because the first thing that's going to come up is A, the next thing that's going to come up is B, and we said that the reason B is because it was added after A. We just added one letter to A, and so now we have B. So this guy obviously came in after A, so it's older. Or rather, actually, it's newer. This is apologies. This is going to be the exact reverse of our new index, but it's kind of the same concept here where you would just load it in reverse. So no big deal. You would just read backwards through the edges list to get your new index. Cool. And then similarly, the same exact thing is happening recursively right over here. So if I actually look at these two children nodes over here, I know that AB is newer than AA. And that's going to really quickly allow us to figure out the newest comments per comment even. Cool. The next option to build this base table out is instead of just doing it using a graph database, we can actually use a normal database. So this is the solution that I touched upon a lot more in that kind of Twitter and Reddit video. And the main idea here is we can actually just use a generic index. Since this isn't a full graph and it's effectively just a tree, we can very much smartly organize our nodes via smart naming in order to properly put them down in an index and find nodes easily. So how would this work? Let's imagine we have this root node and it's got the ID of A. Well, its first child is going to be given the same exact prefix of its parent, so in this case A, and then since it's the first child, we're going to add A. The second child is going to have the same prefix as the parent, A, and then we're going to add B. And we can do the same exact thing in the children of children. So we start again with the prefix equal to the parent's ID, and then add A, and then we do the same exact thing over here. Oh wait, second child, now we add B. And so the idea now is that if you recall, an index in a traditional database is really just sorting out the data, right? So all of a sudden, if we sort these things in alphabetical order, we get ourselves with this data right here. And so now it actually becomes really easy to do like a typical depth first search. Because if I say, I want this entire tree of comments right here, all I have to do is run a range query on our index from A through AAB, and we get really nice data locality because they're all next to one another on disk. And then, of course, you might be thinking to yourself, well, Jordan, there are actually going to be a lot more comments than 26 per level. You probably can't just do A through Z. You're right, I probably can't. But if I did do 0 through 9 and A through Z, that would give me 36 combinations. If I did 4 of those per level, so instead of being A, this guy could be like, 9B, D7 or something like that. That would allow us 36 combinations to the fourth, which is 1.7 million combinations per level. And then, for example, its first child would be like 9B, D7, C, Z, 12, or something like that, where you would, keep the parent's prefix, and then you would go ahead and append something new. Cool. So hopefully that makes sense. And if you notice, this again, like the graph database, is going to maintain that new ordering naturally, because we basically just do the reverse of the traversal, right? So AB, we know, is newer than AA. AAB is newer than AAA. And so we can really easily go down recursively and basically figure out what the newest comment is at each level, pull that, and then pull whatever children it has, or the first newest children of it. Cool. Hopefully that makes sense thus far. So basically, by just building out this, what I would call source of truth table, we already have a really good index for quickly returning the newest comments back to our users. So that's kind of already handled for us. So now the question is, well, we've provided two possible approaches. We've provided the graph database approach, and we've also provided the relational database approach. Which should we actually go ahead and use? So the nice thing about our relational database, like I mentioned, is that, just going back up a slide, if we wanted to do a depth first search on this guy, it's super easy, because everything that is actually a child is right next to its parent, right? This guy is a child of this guy, which is a child of this guy. This guy is a child of this guy, which is a child of this guy. And so you get really nice data locality doing depth first searches. On the contrary, if for whatever reason I wanted to do a breadth first search, basically I start here and then I go here and then I go here, all of a sudden we're jumping around quite a bit on our index, right? I have to go here and then I have to go here. And obviously the more nodes there are in the graph, the worse that's going to get. And then all of a sudden your index doesn't actually help you out very much. So I would say this. If you definitely know that you're only going to be doing depth first type of queries, the relational index that I built is going to help a lot. If you want to be able to do generalizable queries, well, maybe it might not be so good. Now, if you recall, like I mentioned, graph databases are not going to be that fast in absolute terms because of the fact that you're jumping around disk all the time, right? You don't get good data locality. It's still O of one time to find your next node, but it takes a long time to actually go to that actual address on disk. So if we're just doing breadth first search, I would say, a depth first search, I would say we should stick to our non-graph database. But if we want to be able to do basically arbitrary queries, I think the graph database is going to be our move. Cool. And then of course, take this all with a grain of salt. You have to benchmark in reality, look at your actual use cases, and then come back to me. Nothing that I say here actually has a good amount of data to back it up. This is all purely theoretical. Cool. So we've now spoken about how we would build a new index for comments. Let's talk about our top index. So like I mentioned, top comments are those that are sorted by the most upvotes at every single level, right? And the idea here is that, well, if we wanted to actually use a typical index, we could do that in absolute terms, right? So we could very easily build an index to show us the top comments across all comments. But to do so at every single level of our graph, right, is not easy, because then I would have to basically, let's say we've got 3 top level comments. Somehow we'd have to build a bunch of different indices, right? We'd have to build one index for just these guys, and then separately another index for these guys, another index for these guys, another index for these guys. That doesn't work. It's too many indexes. It's just, it doesn't scale properly. So it doesn't make a lot of sense. So what actually are going to be our options here? Well, for one, we could basically just remake the data, but then use a different graph database, and also just have this be for the top comments. And then the other option is to basically keep a secondary index over just the comment IDs. And like I specified before, we would do that in memory, because if it's just the IDs, we mentioned that was around 8 megabytes of storage. That is very, very easy to keep in in memory. God, as you can see, I'm very tired. And so if we keep that whole thing in memory, we can quickly query it and then go back to our source of truth table and get all of the comments that we want. So I've said that very abstractly. Let's go ahead and take a look at how it would actually work in practice. So let's imagine that we wanted a graph database for top comments specifically. So the idea is, if I have this main comment right here, so comment 1, and now it's got 3 children comments, 1, 2, and 3. The idea is we want our edges to be ordered by the number of upvotes that each of those child comments has, so that we're making sure that we pull them in the right order. This is going to allow us to make faster reads. If they weren't in the right order, we could write really quickly to this graph. However, when it came time to read, every single read query would have to basically sort all of these edges, 12, 6, and -2. And that would be bad, because if they were unsorted, now all of a sudden you're having to do an n log n sort over the number of child comments, which can be slow. Cool, so ideally we want to do most of the work on the right path. So just going over here, how would this actually look? A write comes in. Let's say all of a sudden I just added 7 upvotes to this guy. So now instead of being at 6, it's going to be at +13. Now what we would actually want to do is reorder our edges list from comment 1, which previously had, let's call these guys A, B, and C. So previously we said, okay, the first comment you want to show from comment 1 is A, then you want to show B, then you want to show C. Oh wait, now all of a sudden B has more upvotes than C, or rather than A, so let's go ahead and modify this thing so that it's B, A, C, because now this guy is the most popular. And that way we make sure that, if we're ever just looking for the top comment of comment 1, that we're just going to be grabbing B as opposed to A. Cool, and then we have to do that same thing on every single write process. So if for whatever reason I were to write to this guy and add 7 over here, and let's call this guy, I don't know, BA and BB. Previously the order of edges was BA and BB. Now, however, BB is actually more popular, so it's going to go BB, BA. Cool. Hopefully that makes enough sense there. The point is you're doing a little bit of extra work on the right path, maintaining your sorted list of edges on every single write, so that when it comes time to read, you can just go ahead and grab those edges properly without having to actually sort all of them. This is good, especially when you have limit queries, because it means that you're not going to have to go through the whole list and sort it. Cool. So that is the option where we basically effectively maintain a full graph of comments in a secondary graph database where the data is denormalized. In the second option, we can actually just do so in a normalized manner, where rather than holding the whole graph on disk, we actually hold the whole graph in memory, but it's just the IDs, right? So like I mentioned, in theory, in this approach, I would actually have the comment associated with each of these, like Jordan, you're handsome. And it's going to be stored right there. But in this guy, it would just be, hey, this is ID C over here. And then let's say I decide that C is the top comment. I'm going to go over to the database and say, hey, get me those writes in particular and fetch them. And so in that sense, we do actually add some additional read latency, right? Because of the fact that now I have to do an additional join on this database data, and so we have to get one other node involved. That being said, another thing to note is that this potentially makes more sense if our source of truth database is the graph database as opposed to the relational one, because the top comments that we're getting back are not necessarily going to be in a perfect depth-first search configuration that would work well with our relational database. It's probably going to be relatively arbitrary which comments within a chain are the top ones, and so as a result of that, we want to be running arbitrary queries over our source of truth database. It would be better if it were a graph database. Cool. So the idea mainly here is that we're going to do quite literally the same exact thing as over here, right? Where we take in a write, we reorder the edges so that we have faster reads every single time that we want to find the top comments. The one additional optimization that you could in theory make though is that because this is going to be in memory, we can actually add an additional hash map, right? So now we actually have the ID of a node and its corresponding edge so that we can quickly increment the count there. So let's say this guy had 20 upvotes and this guy had 15 and this guy had 10. In the graph database scenario, we would actually have to traverse the graph and find this particular edge to increment the number associated with it. In the in-memory situation, when we make a write and include an upvote, what we can actually do is keep a hash map from the edge of the node, or rather the ID of the node, to the edge itself, and then we can just go ahead and add to that number. Cool, hope that makes sense. It's kind of useful that we have that because otherwise writes can take a really long time. You know, if I'm 10 layers deep in the comment change and I'm trying to add 10 to it, traversing through the graph and finding that is actually going to be somewhat expensive. The next thing to talk about is going to be controversial comments. So the fortunate thing here is, as far as controversial comments go, there isn't actually much to talk about. The one thing to talk about is what is a controversial comment. Well, I'm not going to go for any sort of explicit definition here, but the main idea is a controversial comment is one where there's a lot of upvotes and there's a lot of downvotes, such that, you know, when you add up the sum of the two, that the total score of the comment is close to 0. So I came up with some completely bogus formula right here that could, in theory, calculate it kind of well, because also, in addition to just having a total close to 0, you want to make sure that there were actually a lot of upvotes and a lot of downvotes on that comment. So here's my bogus formula. I'm sure at least one or two of you comment warriors are going to be like, oh, but then if the number of upvotes minus the downvotes is equal to 0, you know, you're not going to have a number, which is why I wrote that note right there. So I thought of you, buddy. But yeah, the idea basically is that we want to be doing the same thing. You know, we generate some controversial score from our upvotes and our downvotes, and we do that on all edges. And then as our controversial score updates, maybe this guy becomes more controversial. You know, this guy all of a sudden becomes more controversial than this guy. Now guess what? We have to flip them so that this guy is the first edge that we traverse to. So again, the idea is mainly just update the weights on the edges, do the work on the right path to reorder our edges list so that we traverse the proper nodes in the right order. And then we do less work on the read path. And it's the same exact thing here as the top comments. We have two options again. We can have a fully separate graph database, or we can have a normalized in-memory graph index of all of the comment IDs in the correct controversial ordering. And then once we actually get the comment IDs that we want to fetch, we can go right back to our source of truth graph database, traverse it as necessary, and get all of the comments that we need. Cool. So the next part of this that I'm going to touch upon is actually going to be hot comments. So unlike the other types of comments that I've spoken about before, hot comments are a little bit more complex. The reason being that the idea here is that hot comments have had a lot of upvotes in the last X minutes, or maybe hour, or something like that. And so the idea is that we're going to have to deploy a separate component or a separate piece of functionality that is ultimately going to keep track of when an upvote, you know, it's been an hour and now that upvote is no longer hot, and so we have to take it away from that comment. Hopefully that makes sense. The idea is, you know, I attribute the upvote to your comment for a bit, an hour passes, guess what? That upvote no longer matters. This is no longer a hot upvote, so we can get rid of it. And so fortunately, this is a pattern that we've seen plenty on this channel before. It's effectively just a sliding window, right? So it's a sliding window with a size of X minutes. And so that all we really have to do is, as upvotes come in, first we can just buffer them in something like Kafka. That way we can use a stateful consumer like Flink. The reason I say use a stateful consumer is that we're maintaining state. If it goes down, we don't want to lose it, right? We do want to eventually be sure to decrement those upvotes again. So it'd be great to use something that is fault tolerant like Flink, where it checkpoints its state on occasion to S3. And that is going to be maintaining a linked list. And the linked list is going to allow us to really, really easily maintain that sliding window. So as an element comes in, we add it to the back of our linked list. We add an upvote to the comment that it's relevant for. On the other hand, we'll also have to check to see if the head of our linked list has been expired, right? We've got a timestamp at each of these points, and so we can see if it's been an hour. If it has, I remove it from the linked list. I go and take the comment ID associated with that element of the linked list, and then I subtract an upvote from the database. So what actually is going on over here in this database? Well, funny enough, it can be literally the same exact thing that we did for both our top and our controversial comments, which is either A, a completely full copy of the graph database, but just, you know, organized such that we prioritize hot comments, or the other option is that we do, again, the in-memory index of just the comment IDs. Cool. So hopefully that makes sense about how we would go ahead and expire an upvote or an expire a downvote. Notice how I said +1 upvote and -1 upvote here. If it was a downvote that was incoming, it would actually be -1 over here and +1 over here. Cool. Now the next part of this is we've basically discussed how we want to go ahead and model our data per comment type. However, how are we actually going to get the data over to all of those different indexes or those replicas of the graph database? Do we want to do it synchronously, meaning when I write a comment, should it go to all 4 of them? Or should we do it in a derived manner, which is I write a comment, it goes to one place, and then eventually we put it everywhere else? Well, the first question is, should we do it synchronously? My answer, as per usual, is no, we probably shouldn't. Why is that? Well, for starters, it may require a 2-phase commit. It's hard to guarantee that all of these guys, all of these 4 different tables are going to be on the same physical node. We could probably do it, but then now all of a sudden we have to store more data there. And so even if we did do that, it could be slow in terms of contention, right? We have to wait for all of those transactions to go through. It involves grabbing a lot of locks. And the bigger thing is that, like I mentioned this kind of towards the beginning of the video, we don't actually need to keep all 4 of these views perfectly consistent. It doesn't really matter, as long as they're eventually consistent, right? As long as they'll catch up to one another, and as long as each individually is causally consistent, we should be good to go. So the next thing I'm going to touch on quickly is, okay, we're going to do some form of derived data, but before we even do any of that, how can we actually make sure that we keep all of these views causally consistent? And then we'll talk about eventual consistency. Cool. So the question first is, what is causal consistency? Now, if you've been watching this channel long enough, you probably know by now, but let's go ahead and lay it out. So the first thing is that, again, like I covered before, if you add a comment to a table, its parent needs to exist. If I add this guy over here, and there's no comment for this guy, even though it exists in some other table, we're going to be like WTF. The user is not going to understand what's happening. The database is going to throw a fit. It's not going to be good, so we want to avoid that. The next thing is that, well, if an upvote or a downvote were to come in, the comment on it, right? So if I upvote a comment on my client, and then I send that upvote to one of my databases, of which there could be many, the comment that I upvoted needs to exist. If it doesn't, that's not going to make a lot of sense. Our database is going to throw a fit. So again, if we just have comment A over here, and then we see +1 on comment B, that would be bad. Cool. So what are a couple of different options that we could do? I'm going to cover 3 of them. The reason being that I first covered 2, thought that was good, realized they weren't good, and I was like, oh wait, here's a third solution that works much better. So we're going to cover the first 2, discuss why they're bad, and then do the third. Cool. So the first 2 are these. We could basically put every single incoming comment, every single incoming upvote, and every single incoming downvote on the same Kafka queue, sharded by our postId. Why does this work? Well, for starters, the nice thing about Kafka queues is that they only have a single consumer and they are completely ordered. And so as a result of that, if I have a comment that exists such that you can make a child comment of it or you can upvote it, I know that that comment will be in the Kafka queue before your child comment or before your upvote of that one. And so the nice thing about that is that then I don't have to worry about causal consistency. The problem there is that that probably works fine for the comments alone. There can be a lot of upvotes and downvotes. If you think about it, there are comments that have thousands of upvotes and downvotes, and there can be thousands of comments, which means there can be millions of upvotes and downvotes for a single post, and that could potentially overwhelm our single Kafka queue. So what could we actually do differently there? Well, one option would be that we basically take all of our new comments, we write them synchronously to all 4 of our comment views, and then from there we can also process our upvotes and downvotes on multiple different Kafka queues, because we know that the comment that they're going to be on already exists in our different comment indexes. That being said, again, writing things synchronously involves some sort of transaction, and if it's a distributed transaction, that's even worse. It's just a lot of locks to grab. It's really going to slow down writes, and that's not something that we want. So here I'm going to illustrate those 2 solutions, which again, I now realize are both bad, and hence I've made a third one right after this. So don't focus on this one too hard. Imagine we have our source of truth comments database. Imagine we have our upvotes database. One possible solution, like I mentioned, is to just put everything in the same Kafka queue via change data capture, all of which is going to be partitioned on postId. and then that goes into Flink, and then Flink is going to update our derived views accordingly. Cool. That seems easy enough, right? So the main idea here is that, you know, all of our upvotes are coming in as like a user and then a comment ID. And on Flink, we would just be aggregating those for counts for comment ID. You know, comment 1 has 10, comment 2 has 20, and that's just going to reduce the number of writes that we actually have to make to each of our derived views. So that's going to be useful for us. Cool. Again, though, it is possible we have too much data for one Kafka queue to handle because we're sharding by post IDs. There are a lot of upvotes and a lot of downvotes. What could be better is if we actually just first wrote all of the comments to both our source of truth table and the derived views, and then this way we can have our upvotes database go not just through one Kafka queue, but potentially to multiple different Kafka queues, thus balancing the load, have multiple different Flink consumers. You know, this time now we're sharding on comment ID as opposed to post ID, which is more granular. So this is all comment ID. And then we're going to go ahead and finally upload all of those counts to our derived views. Again, like I mentioned, this part problematic because that is a write to 4 places at once. We don't like to have to do that. That's bad. So what does Jordan do instead? Well, he goes ahead and makes something that is completely overcomplicated that he loves. So what does it look like? Well, basically what we're going to do is this. We have our comments database. We mentioned there are probably not going to be that many comments for a particular post, up to 1 million, but they're probably going to be relatively sparse in terms of when they're being made. It's not like 1 million per second. So again, we have our comment database. All of those comments are flooding into Kafka, sharded on a post ID so that they're all going to the same Flink node. In Flink, we're just going to do the following. Take in a comment, put it in our derived comment views over here, where these comment views are the ones for top, controversial, and hot. The next thing that we're going to go ahead and do is basically say, oh, you know what? I just received an incoming comment. We're going to take that comment ID. We're going to throw it in this queue over here, which is sharded on post ID and comment ID. So basically, we're going to take our post ID and comment ID that just came into Flink on the comments path and put it into the upvotes path. So now the thing to note is that, again, post ID and comment ID is far more granular. This is going to be handling far fewer events rather than a Kafka queue that is sharded by just post ID and has to handle all of those uploads for a given post. Now what we can do is say, okay, let's say comment 1 has 150 upvotes. However, we're also keeping track of whether comment 1 is present or not. And we'll know when it's present because it actually just comes through this Kafka queue. It's present because it's been processed by Flink, goes through the Kafka queue, and flows into Spark Streaming. So we're actually not going to go ahead and upload our upvote counts to our derived views until comment 1 makes its way to Spark Streaming. So basically once it does, we see it, we say true. Now we have code that says, oh, you know what, the comment is present. We can go ahead and upload these guys to Spark Streaming, and now we're causally consistent because we're only uploading the upvotes once the comment actually exists in all of these derived comment views. Because the first thing that we do is put the comment in the derived comment views, and then we put the comment in Kafka to go down to Spark Streaming. Hopefully that makes sense. It's a bit convoluted, I know, but it does work, and the stream processing and actual determinism of all these stateful consumers makes our life pretty easy when getting this done. Cool. The last question, or last thing to talk about before I really go into the full-on design, is the Upvotes database. So this is a component that I kind of glossed over right here. We have our comment database, which I spoke about plenty already. That's just our source of truth database. But the Upvote database, what is that? Well, upvotes are pretty simple in terms of their schema. I would think that basically you would say, okay, here's our user field, here's our post field, here's our comment ID field, and then here's whether it was an upvote or a downvote. So that's going to be our database schema, and the nice thing about that is that now all of a sudden as long as we shard by our user ID and our post ID for a given post. If I'm a user and I load that post, I can really quickly see all of the IDs of comments that I've upvoted, and so my client can quickly show me whether or not I've upvoted them, which is going to be very useful. Now, of course, like I mentioned, this alone is not going to basically store all of the counts of upvotes and downvotes on each comment. That's why we have this whole convoluted change data capture thing right over here, so that we can aggregate the counts in Spark Streaming and then upload them accordingly, both to our derived views and also similarly to our actual source of truth comment database. We want to denormalize the comment counts, otherwise we're going to have to do a massive distributed query to figure out how many users have actually upvoted a given comment, and that would be very slow. And of course, it's okay if this is eventually consistent, or it takes a while to get the right count. It doesn't really matter. I don't care if a comment has 1,000 upvotes or 1,001 upvotes. Cool. So going back here again, the main idea is we want to be sharding by the user ID and the post ID, so that when I load a given post, I can quickly find all the comments that I've upvoted or that I have downvoted. Now, the main idea from here is that then we would use the change data capture from these tables, and then these can go into Kafka and Flink, or Kafka and Spark Streaming, whatever you want to do, and you basically would just aggregate those into the upvote and downvote score per comment. The point is, as opposed to sharding by the user ID and the post ID of every upvote and downvote in that Kafka queue, we would actually shard on the post ID and the comment ID, so that we can do easy aggregation in our stateful consumer. That is going to make a lot more sense, so that we can have all of those upvotes and downvotes on a single node for a single comment of a single post. Great. Sorry, this is getting so convoluted. Makes sense to me. We'll see if it makes sense for you guys. The next aspect of this is my obligatory caching slide. The reason I'm doing this is because if you were to do an interview about Reddit comments and you didn't at some point mention caching, you would probably be in trouble. I don't really want to talk about it, but I'm going to do it anyway. The idea here is pretty simple. For a lot of hot posts, or just for posts in general, you probably want to cache some initial comments, right? Maybe the first 10 of the top view, the new view, the hot view, and the controversial view, so that the first time someone clicks over to one of those, we can load that up really quickly. And you can either pre-push that into our cache, or you can just do a write around cache where we first write over here, then we attempt to read, right? We get a cache miss, and then it loads the data into our cache such that now we're populated. So those are a couple of valid options. And again, like I mentioned, ideally we've got basically the first view of the new, the hot, the controversial, and the top comments for a given post. And then another client-side optimization that we can in theory do is, if there are a few different buttons to load more comments, once we've loaded that first set of comments, we could begin to prefetch the next set of comments before we even click that button. But that's for a whole different interview, maybe a front-end one, who knows. Cool. I also think that write-back commenting is probably not the move here, or write-back caching. Even though it would speed up the writes, A, one, we care a lot more about reads, and B, is that we want everything to ultimately go through our change data capture, and so in order for it to do that, it needs to first go into our database. So we definitely want to be writing to the database. We could do a write-through cache, but I just don't think we care about cache consistency that much. I feel like write-back, or write-around is the clear win here. Cool. And then finally, right before my voice gives out on me, we're going to be doing a final overview of the design. I'm going to go very slowly here. Hopefully it is going to make everything that I've poorly explained throughout the video a little bit more understandable. Okay, so the first aspect of this is going to be our comment service. When I write a comment, it goes through there, and the first place that it goes to is our source of truth database. Like I mentioned, the nice thing about our source of truth database is that it incidentally serves as a good index for the new comments. Effectively, it's just the exact opposite of new comments. Older comments are going to come first in that source of truth database. Like I mentioned, it would be nice to have Neo4j here because we sometimes want to be able to run arbitrary queries and just get comments with a given ID. If we wanted to run a breadth-first search sometimes as opposed to a depth-first search, using a typical index is not going to be very good for us. So of course here, we want this entire graph on the same node. Otherwise, we're going to be in for a world of pain doing a bunch of distributed reads. So in order to achieve that, we should probably make it so that all of our comments are sharded by their post ID. So for a single post, we want those all in the same table. The next aspect of this is going to be Kafka. Once I write a comment to the source of truth database, I don't want to synchronously update all of our derived comment indexes, but I do want to do it eventually. We throw that comment in Kafka so that we can process it later. This should be a relatively quick write and can be achieved through change data capture. We're going to shard Kafka on our post ID so that all of the comments for a given post can be handled by the same instance of Flink. Cool. From there, what Flink is going to do is basically do a batch write to all of the derived data sources, our top comments view, our controversial view, and our hot view. And basically what this is really just writing the UID, or the ID of the comment, to those places and inserting them into the graph there. So that's going to be step one of this, and then once it gets those acknowledgements, step two is going to be putting it in the Kafka queue to eventually be acknowledged by the Spark streaming upload counter. So I would say this guy is responsible for counting not uploads, but rather upvotes. Cool. Upvotes counter. So again, the nice thing about this Kafka queue is that it is going to be sharded on the post ID and the comment ID. So it actually doesn't matter anymore if your comment is the same post as another comment. All that we really care about is making sure that for a given comment, it and all of its upvotes and downvotes are on the same instance of Spark streaming, and beyond that, we do not care. In that same vein, we want to make sure that all of the upvotes on a particular comment are going to be on the same Spark streaming node. So all that we have to do is from our upvotes table over here, we can very quickly upload those to Kafka, again shard on the post ID and the comment ID, and then basically group those up, right? So over here I would say, comment 1 has a score of +10, and have we seen it? Yes, we have. Now we can go ahead and throw that in all of these different indexes and update the edge score right there and possibly reorder them due to that write. Cool. The reason I also say Spark streaming here is I think mini batching could be good. We don't want to do an upload to all of our derived indexes on every single upvote or downvote, but rather we want to get a bunch at a time, aggregate them, and then change the counts over there. I haven't yet gone through the upvotes table. The reason the upvotes table is MySQL is because the data model is very simple. I don't need any sort of graph database or anything like that. All I really care about is that for a given user and a given post ID, I can really quickly figure out what comment IDs they've actually upvoted or downvoted. Hence, we shard on the user ID and the post ID. And of course, when we actually do make an upvote or downvote, that actually just goes right here through our upvote service. The last aspect of this whole thing is that we're going to go ahead and eventually read comments. And when we do, the main thing that we want to be doing is reading them first through potentially one of these views, right? So let's say I wanted to read the top comments for a given post. I would go to the top derived data cache. This would give me a list of comment IDs. Comment ID. And then after I get my list of comment IDs, I would go right over to the source of truth database, I would fetch those, and then I would have them returned to me through the comment cache, which is probably just going to be Redis. We can shard that by our post ID. And then, of course, the idea here is that we just want to use LRU, right? So as that thing gets filled up, we just throw out the least recently used entry. Cool, guys. This was a lot longer than I was expecting it to be. My throat is killing me. I want to go to bed. I imagine you all do too. But it's been real. Thank you guys for all the support on this channel. You keep me going every day with it, and I'm really enjoying doing it. So let's keep up the great work. See you guys soon.